but we'll have time for questions at the end as well. It's sort of pretty. I'm fairly flexible, but I was thinking of basically about half an hour of talk, and then as long as you like for questions, really. So I hope you can all hear me. And I guess I'll start. I thought I'd start off with my sort of background. I guess I did chemistry and physics as a degree, and then did a PhD in surface science, which was in the physics department of Liverpool University. I was looking at semiconductor surfaces and at a bit of metals and alloys. Then I went off to work for a mass spectrometer company. So started off as an engineer there and ended up in the R&D, research and development. So that was like modeling ions flying around in electrostatics and this, that and the other. For that, then I moved into renewables and was an assessor and consultant for some renewable projects and energy efficiency projects. And then recently I did sort of redid, I suppose, an MSc in fusion energy at York University, which has got a centre for fusion and plasma physics, and did a project with Tokamak Energy as part of that. And then they offered me a job, which was very nice. So I've been with Tokamak Energy just over a year. And I work in the sort of plasma-facing surfaces team. And the idea of the talk here is to give you a few of the sort of challenges in the fusion industry of what we're sort of facing. There are lots of challenges, engineering challenges, and as happens, I suppose, in every engineering company, we're all separated out and split into our sort of specialities. So I won't cover. Well, I might mention a few of the other difficulties, because it's quite hard, fusion. So I thought I'd start off, what is fusion energy? Most of you may know this already. Fusion energy has been going on for billions of years in the sun and other stars. It's basically the source of all our power, if you include things like fossil fuels laid down by photosynthesis. What's happening in the sun? Can you see my pointer? Here, I'm just wiggling it around. Well,
yeah, we can see that, Mike. Yeah.
Thanks. So what's happening in the sun is basically hydrogen is fusing together with helium, and it emits out 26.8 mega electron volts of energy when it does that. Hydrogen's got a mass of 1, and it ends up with helium with a mass of 4. So that's obviously different from nuclear power stations that we have on Earth, where they split uranium and a heavy isotope and release energy by splitting the atom. I think this is fairly well known. The temperature of the sun is about 15 million degrees in the middle. So that's the sort of temperature this reaction is taking place at. But you've also got the effects of gravity, so the immense pressures, because the sun is so big, that contributes to it as well, which means that that gravity and pressure, it makes it very hard for us to do that on Earth. So at some point, the fusion community realised that we can overcome this problem by using isotopes of hydrogen. And this graph down at the bottom here, you'll see that there are lines. This is the cross-section of reaction, which gives us our reaction rate. The blue line here, you'll notice, has a peak, and that's deuterium and tritium. There are other isotopes of hydrogen, deuterium, deuterium, and of course, hydrogen will be way over to the sort of high energy side at a sort of Earth-like gravity. But in the lab, you'll see, so this is billions of degrees, so that's 100 million degrees. So you have to get over 100 million degrees, and then you start getting towards this peak for deuterium, tritium. So fusion on Earth has been done with deuterium, tritium, and this is the reaction that takes place. Deuterium hits a tritium, it makes a helium and a neutron, and that releases 17.6 mega electron volts, which is a lot of energy still. Generally speaking, what we're aiming to do is this helium is going to have a lot of energy that's then going to go and heat our plasma. The neutron then takes away a chunk of the energy, which would be used to heat up the wall of the vessel, and that in turn heats up water to run a steam turbine and generate electricity. So what we are needing to do is get this up to over 100 million degrees, which is very hot. So the way that that's done, one of the ways, there are other ways that fusion's being attempted, but one of the most developed, I think probably the most developed, you could say, is the Tokamak, a Russian invention, been around since the 60s. And the idea is at these high temperatures, all of your atoms have become ionized and it's become a plasma. So the electrons are stripped off. So you have hydrogen ions, deuterium ions, and tritium ions, and electrons. Because they're ions, they're charged and they're affected by the electromagnetic fields. So what we do is we put magnets around them like this, and then you can confine them into this sort of pink donut. That's basically the idea. We put this under vacuum as well because you don't want these to react with anything. So what we're trying to do is, if we're trying to hold this at 100 million degrees, you don't want it hitting any air, nitrogen or oxygen or anything like that. So the whole thing is in a vacuum chamber. And also the magnetic confinement means that you can keep these ions away from hitting the walls of the vessel, because if they hit the walls of the vessel, obviously they're losing energy and they're not confined. So that's the sort of theoretical view. And this picture on the right is a sketch of JET, the Joint European Torus, which is at Culham in Oxfordshire. This is a European funded project that involves all of the European countries to some or lesser extent, and has been around since late 80s, early 90s, I guess. You'll see from the scale, this is a person size, so this thing is big. But you've got the elements here. These big metal structures are electromagnets going round, similar to the sketch here. You've got your vacuum vessel inside, and the plasma is circulating inside this donut. It's a torus. It's called a tokamak, which is a sort of Russian word, which I can't remember what it actually stands for. But so it's big. Now, JET held the record for fusion performance in 1997, and then it's just recently broken that after 25 years of more development. It's just gone ahead and broken its previous record and now holds the record for the largest fusion output. So they've done fusion in here with deuterium and tritium. There are lots of engineering challenges, as you might imagine. Obviously, building the whole thing, powering it, the plasma-facing walls receiving damage, and of course the neutrons, and handling tritium. That's one of them. Tritium is radioactive, and also there's a lot to do with the remote handling, because once the radioactive tritium's been in here and some neutrons have irradiated the surface, you're going to get activated materials, which will be radioactive as well. So the process itself isn't radioactive. The helium you're making, it's not like you're making nuclear waste, and the half-life of any radioactive material you're making is very short. Nuclear fission power stations have, what, the waste there is sort of 20,000 years half-life, and our half-lives are a few years, really. So there isn't really a radioactive problem with the long term, but you have to have some sort of remote handling, which is some kind of robot arm that might go inside here and replace damaged tiles and that sort of thing. So they've been working on all of this stuff at JET for the last 30 odd years. So that's JET. That's government funded, and it's down in Culham. This is Tokamak Energy, the company I work for. And we have built what's called a spherical tokamak. This is a picture of it, and it's called ST40. So basically a spherical tokamak is, if you take this picture here of the donut and you shrink down that the radius so that your plasma in the middle is almost touching, so you've got a center column down the middle. It's very, very small, and this stops being a donut and ends up more like a sphere. The advantages of this is that it's smaller, which makes it cheaper. It makes it easier to make, faster to make, and your surfaces aren't as big. So if you're going to have to put some sort of expensive material on them to armor them, it's cheaper. and quicker. So we've built this device. We've just this is a press release that came out only last month when Tokamak Energy achieved 100 million degrees. So we have only recently, but successfully, managed to get 100 million degrees. So we now have, this machine has made the temperature needed for fusion to take place, which is good news and a really important milestone. So you have to get your temperature up to 100 million or more, but you also need to get up the plasma density in order to get the collisions that you need, and so that's the next step. We weren't really supposed to or allowed to say to the press that we have actually done fusion in here, but we have detected neutrons, which means that fusion has taken place. If we go back to this, so have a look at that graph there. At 100 million degrees, you've got you're aiming for this peak here, but we were using deuterium. So the cross sections and the reaction rates are probably 1,000 times less, but they still occur, and we did detect neutrons coming out of it. So we have actually done fusion, but we've been told not to say that to the press, as it were, because as soon as you say, oh, we've done fusion, they might sort of say, oh, you've cracked it, when we haven't. We've got a long way to go, but fusion reactions have occurred inside that, and it's really a key milestone there to get over the 100 million degrees. So I thought I'd explain the bit I work on. Here's another picture of the tokamak, and you've got your core plasma in the middle, going round and round in a donut shape. Now, it's been confined by the magnetic fields, but inevitably what happens is some of those ions will emerge from the core plasma and come out, and they will hit this outer wall of the vacuum chamber. As they are very, very hot, that will cause sputtering and melting, possibly. And as soon as that happens, you've got metal particles, which are very high mass, flying around, and they disrupt this confinement of the core plasma. They radiate away energy and cause all sorts of trouble. So at some point, I don't know, 20 years ago, something like that, maybe a bit more than that, the idea of the diverted plasma was born, where you put some extra magnetic coils down at the bottom here, and what happens is the magnetic field crosses over. It crosses at this point, and so that what happens is that any ions that are in this central part, as they move out towards the edge, instead of hitting the wall, the transport is much faster down the magnetic field lines. So they come down to this point, cross over, and fly down these two bits, which are called the legs, the diverter legs, and they hit the diverter targets, which are at the bottom. They're still going to cause possibly melting, hopefully not melting, but possibly melting, sputtering and whatnot down here. We have various mechanisms to try and reduce the energy of these things, but the idea of these are more like sacrificial plates, and by putting pumping down here, you can pump away any debris and stuff that's being flung off your surface much more easily, and handle it down there, and it doesn't fly back up. So you've got a big vacuum pump down at the bottom here, and it's trying to stop this stuff from floating back up and screwing up your core plasma. This thing is called the scrape off layer, because it scrapes off debris. So that's helium from your reactions, and hydrogen, deuterium and tritium ions mainly. And so I work in the diverter team, and the two challenges there, engineering wise, are of course the heat. So we have a cooling system that we're designing to cool these plates so they don't melt, hopefully. And then the other problem is erosion, because you're zapping this thing with a beam of ions, which is known to erode. Oh, there we go. They're known to erode surfaces, metal surfaces. And our big problem is, of course, what we could do is just accept that, and every time that these things wear out, we turn the machine off and swap them out as sacrificial parts. However, this leads to a large downtime, and in a commercial power plant, you don't want to be shutting that down. So we are trying to keep these surfaces going for as long as possible by understanding how erosion happens, what's causing erosion, and trying to minimize the erosion on these plates. So my job has been to try and make a model of this, like a computer predictive model, and then compare the theory to experiment. This is the sources of erosion. Abrasion is the one at the top. I sincerely hope we never see this. This is when something's rubbing on your surface. This should never happen because we're in a vacuum chamber, and if there's any big lumps of metal flying around rubbing the surface, we've got a huge problem. So that should never happen. Then you've got evaporation and melting, which happens at the high temperatures. So the other members of my team, as I said, are working on things like heat sinks and cooling to reduce those problems. And then the other sort of source of erosion is sputtering. I've got a bit more on sputtering here. What's happening in sputtering is that ions are coming down and they're hitting the surface. The surface is made up of a lattice. This is a metal. Could be steel. Could be something else. And what happens is there's various different mechanisms. But this one, for example, the ion hits this atom, which has been nicely bound in the lattice, gives it enough energy to escape its binding energy. It flies around a bit, repels off, and it rebounds out of the surface. So this atom then flies away. There's a whole bunch of these other ones as well, with cascades and all sorts of other things. But the basic upshot of it is an ion's going in, and if it's got enough energy, or it happens to hit at the right angle and give enough energy to one atom, you're going to lose atoms from the top surface. And of course, once you've lost enough from your top layer, that's one layer of atoms gone, and then another and another and another will erode the surface. And we have a number which is the sputter yield. This is the number of sputtered atoms coming off your surface for each incident ion. So if the sputter yield equals 1, that means that for every ion hitting this surface, you're going to lose an atom from the surface. Now, our flows are about 10 to the 19 ions per second, and I did do a sort of back of the envelope calculation. If we've got 10 to the 19 ions and that erodes, the sputter yield is 1, so we're eroding 10 to the 19 atoms per second. I think a millimetre of surface lasts for about 3 hours. Or it could be 30 hours, that sort of order of magnitude, so about a day. So if the sputter yield is 1, we're in big trouble, because that's the diverter's going to be about 5 mil thick. So you're going to wear through this diverter in perhaps 5 days, which is no good. Whereas, of course, if the sputter yield is down at something like 0.01 or 10 to the -3 or something like that, you extend this lifetime of the diverter out to months, well, years, preferably. Thought I'd say a bit about the materials. We've actually ended up choosing tungsten or possibly molybdenum, a refractory metal. Tokamaks in the past have been built with steel surfaces. There's Inconel and there's a material called Eurofur, which has been developed from Tokamaks, which has got lower activated components in it, but also carbon surfaces. So in JET, I mentioned that JET, the Joint European Torus at Culham, held the record in 1997 for the most fusion energy produced. It had all graphite surfaces, so it was using graphite because it's very heat resistant. Unfortunately, they found that they have problems with tritium retention and a thing called chemical sputtering, which is another type of sputtering that erodes those surfaces away really fast. What they then did was they switched the material, and now their diverter is tungsten. So it's taken them 20 years to fit a tungsten diverter. I mean, they've done other things as well, and then redo those experiments with deuterium tritium and it's improved the fusion result, because you don't have these problems. So tritium, as I mentioned before, is radioactive. I think its half-life is about 7 years. So any tritium being retained in your surfaces is a big problem for things like maintenance and stuff. So we use tungsten. It's a refractory metal at very high melting point, work function, good erosion resistance, good thermal conductivity, and has a very low tritium retention. Molybdenum's another one, or other refractory metals might do the trick, but tungsten seems to be the best. Tungsten has the highest melting point of any metal we have. So we've been using tungsten, and here is a bunch of equations. I'm not going to go through them, thank goodness. This is to show that in the literature, sputtering has been looked at before by people much cleverer than me, and there's a variety of equations. And what I've done is basically take the equations from the published literature, put it into a bit of code, so we can a bit of programming, so we can end up drawing curves like these. So this is data that I produced from the literature. This is predicting the sputtering using the available theory, and you'll see what happens is that you get you've got your ion energy here, and so these two curves, you can probably see the big ones here with a high sputter yield. So this is going up to a sputter yield of 1, which, if you remember, is where I said that's bad news. This is for neon and for oxygen. So if we get neon and oxygen in the system, and you get up to an energy of a few thousand EV, that'll just basically eat straight through the diverter in a matter of days. Thankfully, here's deuterium, the yellow line, and tritium's the green one. These are down to 10 to the minus 2 sort of levels, which is much more manageable. And the other exciting feature about this is that it drops right off at low ion energy, which is very useful for us, because it means if we have mechanisms of dropping this ion energy down to maybe 100 EV, we might be able to avoid erosion or minimize it so much, so long as we've just got deuterium, tritium, and helium in there, that erosion doesn't become a problem for us, and our diverter and other plasma-facing surfaces will last for years. So that's the holy grail. We have mechanisms of dropping this this ion energy. So in the core plasma, we've got about 10 keV, so it's up here somewhere. So we've got to drop it by 2 orders of magnitude. There are mechanisms for doing that. One of them, unfortunately, is what we call seeding with neon. We can use nitrogen as well, where you put in a gas. So if I go back to this diagram, where are we? If you put a gas in this area, the ions that are coming in collide with that gas and they lose some energy. So it's a bit of a play-off, because you want the ions to lose energy so that they drop down into this area and they're not causing sputtering. But if you introduce neon, if the neon gets ionized, which it will, you have a bigger sputtering problem. So that's one of the challenges, to work out optimal levels of pumping and gas puffing and stuff like that. So that's our theory that we've developed, and I've got a computer program that will predict this stuff, but is it correct? So the rest of the talk is telling you about some experiments that we've done to see if it actually is. So I've had some samples made. We've got plain tungsten, we've got a tungsten coating with a thermal spray, we've got a tungsten coating with chemical vapor deposition, which is a bit thinner, but it's a more sort of more compact, I guess, coating. And then we've got laser additive solutions that Bradley works for, has made us some additive manufacture samples with tungsten. I thought I'd show those samples. This is the deposition head they have, and it's all rather exciting. There's basically a laser here, and these are powder feeders. So tungsten powder is blown down here. The laser is fired at exactly the right place and exactly the right time to melt the tungsten just right on the surface, and you can basically do 3D printing like this. So that's the aim, is to we've taken the sample, and then what you do is you put a layer of tungsten on top of that, so you now have a surface that you've made with a laser additive manufacture. So if, in theory, once we get this to work, then you can then make any shape you like. So you could take a copper heatsink perhaps and put the tungsten on the top as some kind of armor, or, well, I mean, you could take some sort of steel, put tungsten on again to protect the surface, and it can go in all sorts of, well, you can make, I guess, any shape you like. This is one of the early trials, and you'll see this is the base material and this is the tungsten. It hasn't really bonded, there's cracks and all sorts of things. That's one of the early ones, but by the end of their work, this was the sort of result we were getting. This is a cross section, and this blob on the top is the additive material, and underneath is the substrate. We're putting it on, and you'll see it's bonded. The crystalline structure bonding looks good. The crystals are bigger here. This is the crystal size on the base plate, if you like, but there isn't significant cracking. It's looking pretty good, and that's the kind of thing that the samples look like. If we have a look at them in close-up, this is the sample. In the top corner here, this will be the last bit to be deposited. They use an argon sheath gas to stop oxidation of the surface, which works fine when you're actually depositing, but we think probably what's happened here is as the head's moving across the sample, depositing tungsten like a raster going across, so it probably ended up over here with the argon sheath gas that managed to still protect this from oxidation, but because the rest of the sample was still hot in air, it's oxidized to this green color, which is characteristic of tungsten oxide. If we zoom in, you can see these blobs. It's almost like a series of welds, but there are these little white spots on top, which are probably unmelted powder. This is a scanning electron microscope picture of a plain sheet of tungsten. So you can see the sort of, it does have features, but it's pretty flat. And this is the additive manufacture surface, which isn't so flat and has these blobs here. These are about 50 microns across, which is better. The powder was 50 micron powder, so these are probably unmelted blobs of the tungsten powder, which has ended up sitting on the surface. And if we have a look at ADX, which is an X-ray surface analysis tool, this peak just goes off the top of the scale. That's tungsten. It's mainly tungsten, of course, but there is quite a significant amount of oxide shown by this oxide peak here. So there's quite a bit of oxide on these samples. What we find is, oh, here we go. So what I've been doing is exposing them to ion beams, because in our plasma we basically have ions of helium, hydrogen and hydrogen isotopes. At Huddersfield University they have an ion source, which is kind of shown here, but we've been focusing it and collimating it. As you can see here, this purple beam is the ion beam, so this is helium ions. They're zapped down to land on a sample, which is placed down at the bottom, and we mask it with a molybdenum grid. The idea of that is that you end up with a sample like this. So we have to expose these for about 3 days because tungsten, the reason we're using tungsten is it is pretty resistant to erosion. So actually to see anything that you can measure, actually you can't just do a 1-hour experiment because you just don't see anything. But after 3 days you see a pattern like this, and what's happened is the molybdenum grid has been over this part, and these darker lines are where the grid was. They have been protected, and in between each of the grid wires, this section has been eroded. And when we do a profile with a optical confocal profilometer, what you get is these peaks. So this is the bit that was protected underneath sort of where I'm wiggling the mouse around now. That would have had a bit of molybdenum wire from the grid over the top of it. This section here has been eroded away, and we can measure this drop to measure what the erosion depth has been. Once we've done that, we can calculate from that depth what the sputter yield is. We can also do the same by a mass measurement. So we've got 2 methods, and we use this to work out what the sputter yield is of these samples. These are the results. These were the first set of results. So this yellow line here is my prediction from my code. This blue line is a prediction from another paper in the literature, which uses a different code to predict sputter yield, and the various spots are the different results from the different experiments. So you see we've done quite a lot. I honestly think that these error bars are too small because you can see there's a pretty big spread here. But this sort of initial experiment showed us that it does kind of follow the trend. Maybe you might need to squint your eyes a bit, but it does seem to be doing something like going up, and so it's not a million miles away. It's the right order of magnitude in terms of sputter yield, but in general they are higher than we've predicted, up to about 4 times. The code also gives us angular distribution, so the blue line is my code predictions. So at different angles, you get different sputter yields. It rises up and rises up until you get a very grazing incidence, and then it rises down. Of course, at 90 degrees, it's 0 because the any beam of plasma or ions just flies past it and isn't gonna hit. And so again, the squares, the triangles, and whatnot are different samples being eroded at different angles. And you can see that, so this was a sort of second set of experiments we did, and we refined the technique a little bit by this point. It does, you can definitely, well, in my opinion, you can definitely say this thing is following this sort of trend. It rises up and then it's dropping down at the end there. So it is following again. The experimental results are higher, so there is more sputtering happening than I predicted, but we're within a factor of 4. So that isn't so bad. Not bad for a first go. We can compare the different coatings. What this is supposed to show, so this is run 1, run 2, and run 3, and the blue columns here is the sputter erosion yield under identical conditions. So you'll see they're actually not very consistent at all. It goes up by about 20% and then it drops by about 10% from the first run. And the other coatings are similarly up and down all over the place. So this shows that there's actually considerable error and reproducibility from one run to the next. However, when we average the whole lot over, we basically find that the sputter yield between these different coatings on average is pretty close. And we can say they're not noticeably worse than tungsten. Bearing in mind, some of these are on a copper base, and so the yield of copper is about 10 times what tungsten is. So if copper had migrated to the surface, or if the coating wasn't on the surface and it was copper instead of tungsten, this column would be 10 times as big, which would be so obvious. We could easily spot that. So it's all behaving like tungsten, and it's more or less the same, but the experimental results are very variable. So that was the work at Huddersfield. So let me just scroll back a sec, because I think I was going to say something about the oxide. Oh yeah, once you so these samples here, I haven't got a photo. I thought I maybe had a picture of it, but as soon as you expose these additive manufacture samples to the ion beam, when you take them out, their surface is all really shiny like this. So the what's happened is that it's just the ion beam has cleaned off the oxide, and we know the oxide has a much smaller binding energy than the tungsten that's in the lattice. So this could be why some of these, so the additive manufacturing samples are these crosses. So in a few cases here, that's got a slightly higher yield than the other ones done in the same experiment, because we run 3 samples at once. So this will be one sample run with different samples. So a few cases. So this is probably the oxide coming off, which means that it's eroded away quite quick. So you lose a bit of material. And the other samples don't have that green oxide on, but it does clean up. I mean, they come out looking absolutely beautiful. Here's some more experiments. This is Liverpool University. They in the engineering department have a thing called a Sputter Magnetron. This is a photo of it, and here we have the sample, which is held. This is the plasma source, and you can, well, in this photo, that's the plasma source being on, and the sample is sort of, you can't really see it, but it's held inside this machine. And what we're able to do with this is that we stick the sample, as you can see, angle it in front of the plasma source and expose it. So this is a helium plasma. So the helium plasma is a bit different from the helium ion beam in that the plasma is well, I guess much more diffuse and whatnot than the ion beam is a very focused beam of ions. Can't think of a better word to say than that. So in the plasma, we are able to measure the sputter yield by weight measurement. So we take the weight before and after, and Professor Bradley's team did that for us, or well, they did most of the work, to be honest about it. But we are looking to collaborate with with as many universities and companies as possible to get as much information as possible, because the challenges of doing fusion are very great, and Tokamak Energy is not a huge company, though we're growing very quickly. Anyway, here's the results. The blue line is my code prediction. The orange spots are data from a publication in the literature from a German research institute. So that actually follows my curve pretty good. And the green square crosses are the data from Liverpool from the Sputter Magnetron. And you'll see again, they're following the curve. They're not perfect. They're not exactly on it, but they're okay. So this one that's probably the worst one out is out by a factor of 2. That's not bad. Again, they're a bit bigger than the prediction, but if we can get it within a factor of 2, that's actually quite promising, because we need to know if it's going to be 1 day or if it's going to be 1 year. So if it's a day, actually, if it's half a day or 2 days, it doesn't really matter. It's still a really short time. We've got a problem of swapping out our diverter plates. Whereas if it's a year, if it's 2 years, that's okay still, because it means we can actually, that's more acceptable for a time scale for shutting down and doing maintenance on a future tokamak that's actually being used as a power station, because you've obviously got to earn money from producing electricity. So there's the results from Liverpool. So that's quite promising. We did some other work with a company called Plasma Quest, who manufacture plasma sources. This is an argon plasma, so not a helium plasma, but an argon plasma. Argon is much bigger and has the advantage that it erodes the samples quicker, so you're able to do these experiments a lot faster than the other ones. This was, so we've got the results down at the bottom here. There's a picture of it up here. So this is the plasma source, and then the samples put down at the bottom here, and the plasma is bent through with an electromagnet to hit the samples. Here's a blue line, which is from my code again, and the orange spots are the results from Plasma Quest using the argon plasma. So the code can be changed to work for any, so argon ions, helium ions, hydrogen ions, whatever you like. Just a very simple change in the code, and we can produce these graphs. So again, it kind of follows the right trend. In this case, it is lower as opposed to the other tests that we did, which was higher. This is probably because of the magnetic field. This is a 200 Gauss, so there's a fair magnetic field in here. And this is very interesting because we've of course got electromagnets are confining our plasma, so we have magnetic fields in our tokamak. And in the literature there is stuff which is called prompt redeposition, which is when basically what happens is that any if you're sputtering off material from your sample, if it becomes ionized, it's then subject to a magnetic field, and it can basically be turned round by the magnetic field and pushed back onto the sample and redeposit. So that could be what's happening here. I've been doing a bit of modeling on that, and it looks like it might add up. In which case, that's good news for us, because it means that the actual erosion we see in a magnetized environment will be less than the prediction from this blue line, which is good, better than the other way around. We've compared the coatings again. You'll see, so this run here, these blue squares, L is the additive manufacture one done by LAS, and you'll see it's basically the same as plain tungsten and these different coatings. The orange ones are at different energies. Again, they vary up and down quite a bit, but the coatings we find, so they're all very similar. Additive manufacture behaves pretty similarly to thermal spray and chemical vapor deposition coatings, and in general they're a little bit better. So the sputter yield is a little bit less than our tungsten samples, just normal plain tungsten. So, which is a bit of a surprise, because reports in the literature tend to say that coatings have some level of porosity, which makes them weaker. But we found these ones are a bit better, a bit stronger, or more erosion resistant. So that's interesting and quite promising. So overall, this is looking pretty good. So this brings me to the end. I've gone a bit over half an hour. I do apologise. But the conclusion is we've made a code that estimates our sputter yields, and we've done some experiments which show that it's doing the right sort of trend. We haven't got the numbers bang on, but we've got it within a factor of 2 to 4 probably, which is okay. It would be better if we could develop it to be a bit better. And then I am carrying on working on this work to add in prompt deposition and magnetic fields. A Maxwellian distribution is for the temperature, and Huddersfield University have been building us a second ion gun system here, which will be a lower energy ion gun, because what I'm interested in is that bottom bit where it cuts off, if you remember on the graphs, to see if we can characterize that a bit better. So that brings me to the end of the talk. As I like to say, if you have been, thanks for listening. Yeah, thanks for your time, and thanks for inviting me to come and talk to you. It's been a pleasure, and I guess I'll hand back to Bradley and see if there's any questions.
Brilliant. Thank you, Mike. That was really interesting.
Thanks. I'll keep sharing the screen for now, just in case people have anything they want to bring up.
If anybody's got questions, you can either put them in chat or unmute yourself, whatever you feel comfortable with doing. Yeah, I've just got a question, Mike. So how do you produce the fuel for this?
For fusion?
Yeah.
Well, so we've got right back at the beginning, of course. So deuterium you can get out of seawater. It's actually very common on the Earth, something like 1 in 1,000 or 1 in 10,000 molecules. There's a distillation method, so it's possible to make deuterium quite straightforwardly. Tritium is radioactive with a half-life of 7 years, so it disappears very quickly. There's 2 sources. One is a nuclear reactor in Canada, which produces tritium, and I think that's where JET buys theirs from. It's enormously expensive, but the proposal for fusion in the future is maybe we can see on here. It's not very good, really, but if you have lithium, so the neutron that flies out here, if it hits lithium, it can transform it into tritium. Okay. So by a nuclear reaction, or a transformation. So the aim in the future is to have outside of this, you've got your plasma being confined inside your tokamak, and then research that. I mean, this is yet another area of challenge. Is outside here, you're going to need, your neutrons are all flying out. You're going to have some sort of blanket that contains lithium. That's also capturing the neutrons, which is what you want it to do, because that's getting the heat out. You'd have to have some sort of cooling, and that cooling would go off, I guess, a bit like these pipes, with very hot water or possibly some other substance, which then goes to run a steam turbine and generate the electricity, just the same as a normal power station. But the lithium that's contained in that would get reacted and create tritium. So at some point, what you have to do is then rinse out all your lithium, get the tritium from it, and then feed that tritium back in. So once you've got a sort of starter seed of tritium, it should produce its own. The whole thing is fraught with lots and lots of technical challenges. At Culham, they have a tritium recycling plant, which is being developed to try and do this. But with it being radioactive, well, and an isotope of helium, so hydrogen. Sorry, so hydrogen itself is very difficult to. You've got to have special. If you put hydrogen through copper pipes, like welded, it can seep through and all sorts of things.
Okay.
So it's that's another of the challenges, but
very interesting. So I think we've got a question from John Loughhead. If you want to unmute yourself, John, that's
Yeah, I have. Thank you very much, Mike. Fascinating talk and quite complex. But I did want to actually touch on this question of neutrons, because most of your talk was about ions and the impact on surfaces.
Yes.
From the very limited knowledge I've got of this, you've also got very high energy neutrons flying around.
Yeah.
So my question was in 2 parts. One was, what are the neutrons doing to the plasma-facing surfaces, which are much bigger because they're the confinement of the plasma?
Yeah.
And secondly, I'm guessing you don't really want any of these neutrons to get out of the machine. So how are they, the ones that don't end up producing tritium, going to be contained?
Yeah, well, this is another challenge. Yes, yeah, you're quite right. So you've got these neutrons are coming out because of the mass difference here. The neutrons, I think I'm right in saying, take most of this energy with them. The helium takes, well, it's not a quarter, it's a fifth, isn't it? So most of the energy is coming out. So you've still got 14 MeV, which is an enormous amount in the neutrons. The aim of it is to slow them down in the blanket, capture them, and use that energy to turn it all into heat, which runs your turbines and whatnot, and also, as I mentioned, turn your lithium into tritium, and so you've got a tritium source. But inevitably, that isn't going to all completely happen. Let's have a look at this sort of sketch here. So it's going to fly out. I mean, you're talking about it coming out of the core plasma. It's basically going to fly in all directions. A small amount's going to go down to the diverter, but it's basically going to hit all of these walls. So there's a number of challenges here. First of all, this central solenoid, which runs down the middle, you have to protect that from neutron damage. So basically, this thing needs to have some sort of neutron absorbing material on it, because it'll, after enough neutron damage, I should say that Tokamak Energy is also developing and looking at putting in superconducting magnets here, and those superconducting magnets are damaged by neutrons, so we need shielding on this central part. Basically just stop the neutrons, and we don't really, so long as we stop them, we don't really care about very much else, to prevent the damage to the magnet. But on the outside, yes, you get lots of effects like embrittlement, which you get on tungsten, is known to embrittle when it gets hit by neutrons, and so are steels. So yeah, there is an issue. I mean, you're going to have to have materials that basically allow the neutrons through into your blankets, but then behind that, we're going to need neutron absorbing materials. So there are things. We've been talking to people. High entropy alloys is one thing that's used as neutron shielding, or promising neutron shielding materials. But yeah, you're going to end up with a whole sort of sandwich layers of things doing different jobs in different places. But the problem with neutrons hitting most of this stuff is embrittlement of the metal, basically, which means its lifetime it will then erode away more, and it'll structurally as well. It's going to have to, because we're in magnetic fields, it's under a lot of forces as well. So at some point, you know, so yes, it is a big problem. And we have in my team, there are other people that are doing neutronics.
So could I, Bradley, if you'll permit me, just a very quick clarification. So you've already mentioned, Mike, that these are structural materials. So if you've got embrittlement, you were talking about the diverter plates and the need not to have to replace those too often. Have you currently got any idea of how long the structural elements that form the main tokamak are likely to withstand this neutron bombardment?
Honestly, I don't know. We do, as I say, we've got a neutronics team, and they've shown me some of these models that they have, which are quite amazing. You have a, I don't know if you've seen them, but you basically can model a structure, and then you fire neutrons in, and it whizzes around, displacing all these things, and then popping them back together. Oh, well, they sort of try and fall back into their lattice positions, but they don't normally do it. So it's measured in displacements per atom, and I know that some of the stuff we were looking at with these I think it was the high entropy alloys, can handle 90 dPa, 90 displacements per atom, which is that might be the sort of level. I'm not really an expert in that area, unfortunately, but yeah, there are people working on it, and it is another of the challenges. But it's something we're aware of. But I think these tokamaks need sort of groundbreaking research in probably about 6 or 8 separate areas, if you know what I mean, because the environment's just so harsh. You know, you've got 100 million degrees here, and that's what they often say. You've got 100 million degrees in the middle, which is hotter than the center of the sun. And then if these are superconducting magnets, which they aren't in our machine at the moment, it's going through an upgrade right now. It probably won't have superconducting magnets fitted this time, but probably next time you have to put them in liquid nitrogen or something. So you've got, you know, minus 200 odd here, and so it's kind of ridiculous, really, the sort of extremes that we're trying to get to. But that's the physics. It's got to be like that to make the physics work. But yeah, it's a very valid point. Neutronics is a huge area.
Okay, brilliant. Yeah, thanks for the question, John.
Is there anyone else like to pipe up? I'm quite happy for another few minutes. Or you can finish now if you prefer. I can show you. I'll put an extra slide in at the end, I think, if this is the right one. Oh yeah, here you go. So this is ITER. This is the entire world has come together to build ITER, which is in the south of France, and this is the next generation tokamak, following on from JET. I just wanted to put a couple of photos in because I think this is absolutely amazing. This is enormous. This is absolutely huge. This is a picture of the tokamak itself. It'll be that big. I think it's, what's its radius? Got about 9 meters radius of the plasma, something like that. It's absolutely, but the whole building here is massive. So this is the tokamak pit where it's being built in, and this is the hall where they're assembling stuff, and then they shunt it off down this way. But I mean, you can see, you know, that's a digger truck, a lift, you know, some kind of telehandler type thing. So, you know, people are absolutely tight. It's enormous. And so this part here is one of the wedges that form the sort of segments of the orange, if you like, to be assembled as the tokamak. But it's just the scale of this thing blows my mind. So if you want to have a look at some of this engineering, it's if you go on look for ITER, they've got videos on YouTube and whatnot of them where they're up to. They post quite regularly on the manufacture of this thing. But I think it is the biggest science project in the world at the moment. It's absolutely monstrous, but costs so much. So the aim of Tokamak Energy is to try and develop something small. The idea with the superconducting magnets is that it'll enable us to get a magnetic field, a strong magnetic field in a smaller area, and that's actually going to be achievable for a company like ours to raise the amount of money and build the thing that isn't going to be this size, because there's no way we could afford that. So that's the idea of Tokamak Energy, sort of going a different route, but this is going for the sort of a bit more standard, but just so big. And but Tokamak Energy is hiring, by the way, if anyone on the call is interested in working for this company down in Oxfordshire and has skills or interest in this area, go and have a look at our jobs page, because we are expanding.
So, Mike, could I just come back? I don't want to dominate the discussion, but
Sure.
I mean, you've described some really challenging materials issues and demands on this, and you know, you look at the pictures of ITER, and yet I hear from Cullen that they're going to have a fusion reactor on the grid by 2040. Is your company as optimistic about how quickly some of these big challenges can be met?
Sort of, yes. Tokamak Energies. So we know about climate change and the sort of urgency of the date for going zero carbon was 2030, basically, scientifically speaking. But in the last IPCC report, I think they've said we've got 30 months. Because things are probably moving a bit faster than we thought. So Tokamak Energy's original aim was to make a demonstration power generating tokamak which isn't the same as a fully working power station, in 2030. So, and the idea being that we're a smaller, more nimble, faster company. And for ITER, for example, is funded by government, so they publish all their results. So we can read the papers, and if they say, oh, tungsten's no good, but an alloy of tungsten and such is what we want, or neutron shielding's really great with this high entropy alloy, we can go ahead and use that. So we've got that advantage, but because it's a small, nimble company, you know, the sort of try everything and fail fast is the sort of idea, which seems to be in vogue at the moment, you know, with the companies like SpaceX and whatnot, and seems to be successful. So the aim was, is to make a demonstrator that's actually producing electricity in 2030. So, which is a very short time frame. But the feeling in the company is basically if we don't target ourselves with something really challenging, then you know, we'll just laze around about. You know? So there are other companies. There's one in the States called Commonwealth Fusion, which has got a 2030 deadline as well. And Jeff Bezos has funded another fusion energy company in Oxfordshire, and he's talking about 2030 as well. Although I don't think we really think. Well, I'm not sure what we think about his. He's got a different approach, his company, and there's other fusion projects as well. In America, they've got the National Ignition Facility, which is a big, massive laser thing that fires lasers to compress stuff, and they've achieved fusion in that. They've managed to get deuterium and tritium to fuse, but that's got its own challenges. So yeah, the answer is we're trying for 2030, but hopefully, you know, be nice if we can.
Hope you've got good share options if you make it.
Yeah, that'd be good. But yeah, we'll see. It might end up being a massive collaboration, of course. Who knows? To some extent, if we can provide a zero carbon energy source in the 2030s, you know, that's just such a great thing to do. I think we'd be happy if we've got some intellectual property in the final solution that we can make money out of. It's good enough, isn't it? So yeah.
Brilliant. Yeah, that's great. Thank you, Mike. Thank you, John.
Yeah, thank you.
Yeah, if there's not any more questions, I'll just like to wrap things up. So thank you everybody for attending. I think that was a really good presentation by Mike, and hopefully you all found it interesting. So the South Yorkshire area is quite an active I'm a Key committee, and if anybody's interested in coming along, please feel free to get in touch with me. I think you've probably got my my details on here somewhere. But if not, what I'll do, I'll put my email address in the chat, so you can all get in touch with me if you want.
Bradley, before you do that, I don't have a chat function on my Teams here.
Oh, right, okay.
The chat seems to have been disabled.
Oh, I don't know what's happened there, John.
Maybe it's just me.
Yeah, so has anybody else got that problem?
I do, but I'm on my phone watching, so I'm not sure whether. I thought it was just because I was on my phone that I couldn't see any chat.
Yeah, it's maybe a me problem then. That yeah, okay. Yeah, I'm not 100% sure why that is. Mike, can you see chat at all or not?
I have got a chat thing.
I'd just like to retract my previous statement. I've just found it in a drop-down thing.
Okay.
Somebody
but John, what I can do, I can always send you my email basically if you want.
Great. Okay. Thank you.
So there we go. Brilliant. Yeah, that was really good. Thank you all for coming. Yeah, big thank you to Mike as well.
Nice to meet you.
Thanks very much.
Cheers, everyone.
Thanks a lot. Cheers.
Okay, cheers. Goodbye now. Thanks, Bradley. Much appreciated.
Yeah, no, big thank you to you, Mike. Yeah, that was really good. I think cool. I think everybody get a lot from that. You know, like the sputtering. I myself wasn't fully aware of that effect. So it's good to know that these things exist. I mean, there's obviously people who've got a lot more experience than me. So it's it's good to know.
All right, then. Take care. Have a good Easter weekend then.
Yeah, you too.
Okay, cheers. Bye.
Cheers. Bye.